Good morning, ma. In previous class, we have seen some purification methods of colloids. Under that, we have seen dialysis and electrodialysis. Okay, dialysis only in the presence of electric field, it will be little bit fast. That is called electrodialysis. By seeing that itself, you will understand. Oppositely charged that impurities will be fastly moving towards oppositely charged electrodes. Okay, without that electrodes, the process will be slow. In the presence of the electrodes, the process is fast. Okay, and finally we have ultrafiltration. Let us see that one. Ultrafiltration is the process of separating the colloidal particles from the solvent and soluble solutes present in the colloidal solution by specially prepared filters. By specially prepared filters, we are going to separate the impurities from the colloidal solution. Okay, which are permeable, means allowed to all substances except the colloidal particles. Colloidal particles can pass through ordinary filter paper. Normally in our laboratories we have some filter paper. That filter paper holes will be like slight holes will be there. That holes will allow colloidal particles. Normal filter papers will allow colloidal particles. Then what they are going to do? That normal filter paper is coated with some suitable cream like that, and the hole size is going to be reduced. Let us see that one. Colloidal particles can pass through ordinary filter paper because the pores are too large. Okay. However, the pores of filter paper can be reduced. The pore size will be reduced in size by impregnating with colloidal solution. By impregnating means we are going to coat on that filter paper with this colloidal solution. When we coat that filter paper with this colloidal solution, the size of the pore will be reduced. Okay. However, the pores of filter paper can be reduced in size by impregnating with colloidal solution to stop the flow of colloidal particles. Then, when the hole size is reduced, colloidal particles cannot pass through that one. But electrolytes, impurities can be passing through. In that condition, colloidal particles will be remain in the solution only, and impurities will be gone out. Okay. The usual colloidal is a 4% solution of nitrocellulose. Normal colloidal solution is a 4% solution of nitrocellulose in a mixture of alcohol and ether. Just for information, they won't ask this one. Okay, an ultrafilter paper may be prepared by soaking the filter paper in a colloidal solution, hardening by formaldehyde, and then finally drying it. First they will just soak that normal filter paper in the colloidal solution, 4% cellulose nitro solution. After that it will be hardened by formaldehyde and dried. Thus, by using ultrafilter paper, the colloidal particles are separated from rest of the materials. Okay, ultrafiltration is a slow process. To speed up the process, pressure or suction is applied from the below. Generally, when we pour the solution, the total electrolytes should come out. For that, it will be time required. Then what they will do, they will keep it in a conical flask and they will connect it to suction pump. When it is connected to suction pump, fastly the impurities will be coming out and fastly the colloidal particles will be separated. Okay. Using ultrafilter paper, the colloidal particles are separated from the rest of the particles. Ultrafiltration is a slow process. To speed up the process, pressure or suction is applied. The colloidal particles left on the ultrafilter paper are then stirred with fresh dispersion medium solvent to get a pure colloidal solution. Okay, it is getting in the form of solid. Then it is again mixed with some solvent and it is prepared as colloidal solution. That is about ultrafiltration. Simple thing only. By reading itself we can understand, no problem. Next, properties of colloidal solutions. Correctly, these properties of colloidal solutions we will see in 2 classes. In today's class and one more class. By that, surface chemistry is going to be completed by your Monday's class. Okay, now first one, Various properties exhibited by the colloidal solutions are described below. First one, colloidal properties. Colloidal properties. Colloidal particles being bigger aggregates, the number of particles in a colloidal solution is comparatively small as compared to a true solution. Actually, these colloidal particles, they are in the size little bit big when compared to true solution. To form that much big particle, generally these small particles are aggregated, means will be coming together and they will be formed like a big sized particle. Okay, then what is going to happen for number of particles when compared to true solutions? In true solutions, number of particles are very high when compared to colloidal particles. Actually, all colligative properties are depending on number of solute particles. 4 colligative properties we have in solutions we have seen. Those are relative lowering of vapor pressure, next depression in freezing point, elevation in boiling point, and osmotic pressure. These are the colligative properties we have studied for true solutions. Okay, same thing we are going to apply in colloidal solutions also. If you apply here, as those colligative properties are depending on number of particles, but here colligative properties also depending on number of particles only, but colloidal particles number is small. Then what is going to be happen? Colloidal particles being bigger aggregates, the number of particles in a colloidal solution is comparatively small as compared to a true solution. Okay, hence the values of colligative properties, osmotic pressure, lowering in vapor pressure, depression in freezing point, and elevation in boiling point, are of small order as compared to values shown by true solutions at same concentrations. What is the meaning? In true solutions, that number of particles are very high. Because of that, one small thing, colligative properties are depending on number of particles. Okay, colligative properties are directly proportional to number of particles. Colligative properties are directly proportional to number of particles. When number of particles are increased, colligative properties also increase. In true solution, number of particles are very high, then colligative properties values are high. But in colloidal solutions, those values are less. That means number of particles value will be less. According to that, colligative properties values are also less when compared to true solutions. Okay, so colligative properties of colloidal solutions will be of less order when compared to colligative properties of true solutions, because number of particles in colloidal solutions will be less. That is the reason. Okay ma, this is simple only. Next, second one, Kendall effect. Okay, this is very important. Even after completion of this one, I will show that animation video also, or some experiments were also done. Those also I will send. You can see that one, you can watch that one. Okay, see all of you. Kendall effect. If a homogeneous solution placed in dark is observed in the direction of light, it appears clear. And if it is observed from a direction at right angles to the direction of light beam, it appears perfectly dark. If a homogeneous solution placed in dark is observed in the direction of light, it appears clear. Is observed in the direction of light means, suppose this is the solution we kept. In this way, light is getting. We are also observing from this direction only. Means in what direction light is passing, in the direction only we are also observing. Then when we observe, this is homogeneous solution, means true solution. This light will be passed through this homogeneous solution simply. Then if you observe that light falling on backside screen, that screen is appeared as clear. That screen clearly we can see. Okay, now if a homogeneous solution placed in dark, this is placed in dark, is observed in the direction of light, okay, it appears clear. That means clear solution we can see. If it is observed from a direction at right angles to the direction of light beam, it appears perfectly dark. If you observe the solution, from like this here, in this direction, it will be appeared as dark. Why? The light which is passing through this solution, straightly it is passing through the solution only. It is not traveling in any other direction. Total that room is dark, ma. Total that room is dark. Only one light source is present, one small bulb is present here. From that bulb we are getting light. In what direction the light is passing? Like this it is passing. Okay, if you observe in this direction, I am seeing like this, then I can see the solution clearly. Simply it will pass through the solution. Nothing will be happen to the solution. But if you see from right angle triangle, this is 90 degrees only, like this if I see, nothing we will see because no light is there. No light is falling on the particle, correct or not? Simply light passes through the solution and it is falling on the screen only. If you see the screen, then we can observe. But if you are observing the solution from 90 degrees, we cannot observe anything. Dark, it will be dark. That is the condition for homogeneous solution. Because the particle size present in this homogeneous solution are very small. Very small. Okay, now continuation. Let us see that one. Colloidal solutions viewed in the same way may also appear reasonably clear or translucent by the transmitted light, but they show a mild to strong opalescence. Okay, when viewed at right angles to the passage of light, that is, the path of the beam is illuminated by a bluish light. This effect was first observed by Faraday and later studied in detail by Tyndall effect and is termed as Tyndall effect. Tyndall, the bright cone of the light is called Tyndall cone. Okay, now what is going to be happened? One small example, ma. Let us take any buttermilk or milk in a bottle, our plastic bottle. Normal 10 rupees bottles are there, na? Okay, in that bottle let us take milk or buttermilk. Okay, keep torchlight on that one. Keep torchlight on that one. In another solution, in another glass that plastic bottle, let us take salt solution and keep torch on that salt solution. That one experiment was done in YouTube, ma. That experiment was there. I will send to you. Okay, what we are going to observe, that I am going to say. Before that, one small example. While we are watching movies, okay, we will be sitting in our seats. If you see above like that, light is passing from projector. Is it correct or not? From projector, light is passing like this and it is falling on the screen. Okay, correctly if you observe the path of the light, we can see the dust particles present in the path of the light clearly. We can see the dust particles present in the path of the light clearly. We are observing with 90 degrees, ma. Okay, that in projector room, one person will be sitting. If he observes through the light, he might not see those particles clearly, because he is observing in the direction of the light. We are observing in the direction 90 degrees to the light. Okay, there what is going to be happened? Dust particles which are present in the air are reasonably some medium size, in which they will scatter the light. When that light is falling on that screen, on that particle, that particle is going to scatter. Scatter means it is going to distribute the light in different directions, like this. Then what is going to happen? From that, one beam of light is fallen on our eyes. Okay, that is reflected by which particle? That particle only. When it is reflecting from that particle, we can see that particle clearly. Same scattering will not be happening in true solution, because in true solution the particle is very small. Because of that, this light simply it will pass through the solution only, nothing will be happen. Coming to suspension, in suspension completely the particles are settled at the bottom. If you pass light through that one, half of the solution will be opaque and remaining half will be true solution. Correct or not? In suspension. Then through that true solution, light will be passing without any deflection scattering. Through these sand particles, it will be formed like opaque, means shadow will be happen. Nothing will be there. So suspension will not show Tyndall effect. True solutions will not show Tyndall effect. Only solutions which will show Tyndall effect, that is colloidal solution only. What is meant by Tyndall effect now? The process of scattering of light by colloidal particles. The process of scattering of light by colloidal particles is called Tyndall effect. Okay. Now scientists examine the Tyndall effect by using the experiment. What is that experiment? Let us see here now. He used one light source. From that light is coming in different directions, but he wants to make that into one beam like this. Okay, and he made that beam to be fallen on the particle. This is colloidal solution. Here one particle exactly that on that particle it is fallen, and from here it is scattered. Light is scattered. Okay, we are observing from here in this direction by using microscope. Then we can see the particle, this particle clearly, because this light is there now. It is going to be falling on our eyes, and we are able to see the light clearly. The cone which is happened here, this is called Tyndall cone. From here to here like this, one cone will be happened now. That cone is called Tyndall cone, and this effect is called Tyndall effect. This was first studied by Faraday and later it was developed by Tyndall. That's why this effect is called Tyndall effect. The process of scattering of light by colloidal particles is called Tyndall effect. Okay, now once I will read this one. Colloidal solutions viewed in the same way may also appear reasonably clear or translucent by the transmitted light, but they show a mild to strong opalescence when viewed at right angles. Okay. Right angles to the passage of light, that is, the path of the beam is illuminated by a bluish light. This effect was first observed by Faraday and later studied in detail by Tyndall and is termed as Tyndall effect. The bright cone of the light is called Tyndall cone. Okay, the scattering of light illuminates the path of beam in the colloidal dispersion. That is going to be happen. This process is called Tyndall effect. Okay, not only here. If you go into the caves with small holes, through that small holes sunrays are coming into the caves. If you observe that sunrays path, in the path of the sunrays, if you observe the dust particles, clearly we can see the dust particles. Why? The dust particles are going to scatter the light. Okay, then that scattered light is falling on our eyes and we are able to see the dust particles clearly. Next. Tyndall effect can be observed during the projection of picture in the cinema hall due to scattering of light by dust and smoke particles present there. Tyndall effect is observed only when the following two conditions are satisfied. When the following two conditions are satisfied, then only we can observe the Tyndall effect. What is that first one? The diameter of the dispersed particles is not much smaller than the wavelength of the light used. So definitely we are using light with some wavelength, 10 power minus 2 nanometers, like that we will use. Okay, then the size of the particle also must be in that range, 10 power minus 1, 10 power minus 3 nanometers, like that, means suitable. The light wavelength and size of the particle must be matched, then only scattering will be happen. Second one, refractive indices of the dispersed phase and the dispersion medium differ greatly in magnitude. Definitely dispersed phase and dispersion medium, two different refractive indices are there, ability of bending of light. Okay, those two must be very much variant with magnitude. Okay, these two conditions if they are fulfilled, then only Tyndall effect will be shown. Next, Tyndall effect is used to distinguish between a colloidal and true solutions. Sigmund in 1903 used Tyndall effect to set up an apparatus known as ultramicroscope. An intense beam of light is focused on the colloidal solution contained in a glass vessel. The focus of the light is then observed with a microscope at right angles to the beam. Individual colloidal particles appear as bright stars against a dark background. Individual particles are appeared like bright stars, means they are scattering the light, then they are appeared as very bright colored. Okay, with a dark background. Ultramicroscope does not render the actual colloidal particles visible, but only observe the light scattered by them. Generally, when a vehicle is coming in front of you, okay, with high beam of light, we can observe the beam of light only. The person who is coming, we cannot see that. Like that here also, if you are observing the light in the opposite direction of the light, exactly, okay, then we cannot see the particle clearly. Exactly in the direction of the light, if you see, we can observe the light only. Under microscope, this is happened. Okay. Actually, normally little bit angle different from 90 degrees, if you observe, then we can see the particle clearly. Okay. Next. Thus, ultramicroscope does not provide any information about the size and shape of colloidal particles. This is about second effect, that is called Tyndall effect. Okay, everyone, are you clear now? Okay, ma. We have completed this Tyndall effect also, second one. Till now we have seen two properties. What are those two properties? Colloidal properties and Tyndall effect. Next, third one. Color. The color of colloidal solution depends on the wavelength of light scattered by the dispersed particles. Once again, the color of colloidal solution depends on the wavelength of light scattered by the dispersed particles. The particles which they are going to disperse are scattered. Okay, that light we are using, depending on that light wavelength, it is depending. The color of colloidal solution depends on the wavelength of light scattered by the dispersed particles. The wavelength of light further depends on the size and nature of the particles. Okay, this is interrelated. Color of colloidal solution also changes with the manner in which the observer receives the light. And generally, if you see the sun, normal day, if you observe, it is in yellow color. While it is getting set down, okay, in the west, if you observe, it is in orange, very bright orange color like that. Okay, actually that angle is different. Sun is there only. Earth is rotated now. Because of that rotation, the angle which we are seeing the sun is getting different. Because of that, light passes through the dust particles, refraction, all these properties keep that colors are different. Okay, are you able to understand? Like that here also. Color of colloidal solution also changes with the manner in which the observer receives the light. Okay, depending on the observer receives the light, the color of the colloidal solution also changes. See, they give one example. For example, a mixture of milk and water appears blue when viewed by the reflected light. When we observe by using the reflected light, mixture of milk and water, it appears blue, and red when viewed by the transmitted light. When we observe through transmitted light, okay, if you observe that milk and water mixture, it is observed as red color. Finest gold soul is red in color. As the size of particles increases, it appears purple, then blue, and finally golden. Depending on the wavelength of the light as well as size of the particle. If small size particle is there, scattering will be high. According to that, color will be dispersed in a different way. According to that, color of colloidal solutions will be changed. This is third property, color. Next, fourth property, Brownian movement. Simple one only. We will stop by Brownian movement, four properties. Fifth, sixth, and seventh. Even last, the process of settling of colloidal particles is called coagulation. That one. These three in next class we will complete. Okay, by Monday's class we will complete this chapter. Next. Coming to this Brownian movement, when colloidal solutions are viewed under a powerful ultra microscope, the colloidal particles appear to be in a state of continuous zigzag motion. Actually, these are not very high sized particle as well as very low sized particle. This is a moderate. Okay, because of this moderate size also, smaller particle, they are going to move from one place to another place in a zigzag motion. These colloidal particles will move from one portion to another portion in a zigzag way. Okay, that movement is called Brownian movement because it was observed by Brownian. See, when colloidal solutions are viewed under a powerful ultra microscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of view. This motion was first observed by British botanist Robert Brown and is known as Brownian movement. This motion is independent of the nature of the colloid but depend on the size of the particles and viscosity of the solution. If the viscosity of the solution is high, this movement will be less. Okay, if the viscosity of the solution is less, then movement will be high. As well as if the size of the particles is bigger, it will be slow. Slowly it will move. If the size of the particle is smaller, fastly it will move. But anyways, the zigzag motion is called Brownian movement. This motion is independent of the nature of the colloid but depends on the size of the particles and viscosity of the solution. Smaller the size and lesser the viscosity, faster is the motion. That one I told. Viscosity less. Actually in honey, the particles cannot move easily. But in water, the particles can move easily. Viscosity is less for water. Okay. The Brownian movement has been explained to be due to the unbalanced bombardment of the particles by the molecules of the dispersion medium. The Brownian movement has a stirring effect which does not permit the particles to settle and thus is responsible for the stability of swirls. Okay, because of this movement only, they are in continuous motion and they are not going to be settled. If they are settled, they are formed as precipitate. Then it will be suspension, no longer it will be colloidal. Okay, because of this Brownian movement only, somewhat these colloidal solutions are stable. That one they want to say. Okay, ma? Brownian movement. So today we completed 4 properties. Colligative properties, second one Kendall Effect, third one color and fourth one Brownian motion. 5, 6, 7 and little bit more properties, some points are there. Those things we will complete in Monday's class. Okay, ma? By that surface chemistry chapter will be completed. Now I would like to say one thing, that is, immediately we will not go for P block, D and F block. Okay. I will start with some basics of periodic classification. Monday, Tuesday, Wednesday, Thursday. Okay, Friday. School will be started from Monday, ma. School will be started from Monday. These Tuesday onwards up to Saturday, I will go through periodic classification only. I hope after coming there, I will go through the P block, D and F block elements directly. Those 2 chapters directly I will teach for you. Okay, that is my plan. Let us see what will be happen. According to that we will go through. Okay, so maximum all the chapters are completed except that inorganic P block, D and F block. You have to be very clear and you have to do hard work for getting good marks. That is about today's class. Okay, thank you all.